लाइव स्टार्ट लाइव अवेलेबल ওখানে হ্যাঁ সেন্টার ওখানে ওই যা পাঠানো সেটাকে জাস্ট কপি করতে হবে না সেম লিঙ্কে হবে না কিন্তু লিঙ্কটা মুছে জাস্ট এটাকে oh here is a new link here is a link for the afternoon session and you can live stream link for afternoon session হ্যাঁ কি বলেন লাইভ হ্যাঁ চলে আসবে নিশ্চয়ই আচ্ছা এখান থেকে তুমি লিঙ্কটা নিয়ে নাও কমেন্টটা সেট করে এবার শুনুন হ্যাঁ পেয়েছো এটা পাঠিয়ে দাও জাস্ট সেন্ড করে দিলেই হবে নতুন লিঙ্কটা তো আর গুগল মিটে গিয়ে দেখো ক্যামেরা ঠিকঠাক আসছে কিনা জয়েন হুম ঠিক আছে so let's begin with the afternoon session of day 4 that is we'll proceed to show this but this will be given as short exercises for you to do okay so at first I mean a step to this is to show that so exercise 1 limit s goes to 1 plus s minus 1 times zeta s so show that this is equal to 1 this is an easy exercise and perhaps you can tell how this is happening right we already saw yesterday right that is zeta s is equal to 1 by okay okay let the others proceed a little bit and then so if in the morning or in the tutorial session tomorrow sorry in the tutorial session yesterday we saw a direct application of Abel summation formula which gave this thing right actually in the morning we wrote the entire expression but I mean this was just big of 1 as you saw yesterday right bounded by some constant now if you multiply this with s minus 1 that means s minus 1 times zeta s is equal to 1 plus big O of s minus 1 right okay and now if you let s go to 1 yeah Right, yeah. Okay. Inside big, oh, of course, yes, because this is, yeah, it's bounded by some, okay, this is just bounded by some constant, and if you are multiplying it with s minus 1, then the size is bounded by this, indeed. And we assume that whatever is inside is a positive valued function. Okay, so that's why you need this one, right? Okay, so now this one, as s goes to 1 plus, I mean, from, you cannot say that it is, well, we know that this expression was true for real part of s greater than 1, right? So if we take the limit that s is going to 1, we should take it from the right hand side, right half plane. Okay, and that is giving you 1 here, and here the size is controlled by this one. Okay. So s goes to, I mean, this one should go to 0, and this will converge to 1. Okay, all right. Now suppose this sigma s has a 0 somewhere on the real line, not real line, real part of s equal to 1 line. Okay, that would mean that, okay, let s equal to sigma plus it. So this is exercise 2, p 0 of this, not sigma plus it, because we are saying that it is on the 1 line, so 1 plus it. Okay, be a 0 of zeta s on the line real part of s equal to 1. Okay, oh, this one here is just the conclusion. Okay, now here we are also going to get something like a, I mean, we'll take a limit, but not this time, we will not multiply by s minus 1, but we will do something else. Okay, so consider this limit zeta s. Well, suppose it has a 0, I mean, this be a 0 of zeta s at on this line, and let the order of vanishing of zeta s on this point be m. Okay, so in other words, zeta s has a 0 of order m at this point. Okay, and at 1 plus it be m. Okay, then we take the limit I mean, the first one was easy, and this time what we are going to write, it seems even easier. Okay. So consider this limit zeta s by s minus 1 whole power m, and limit um, s goes to this point. Okay, 1 plus it from the right half plane. Okay, now this limit is not equal to 0. Why? Right. Yes, indeed. It's just the definition of order of vanishing. I mean, that zeta s has order of vanishing m at this point, right? So in particular, I mean, this is actually trivial. So equal to some constant, which is not equal to 0. Okay. Then that would imply that the limit, write S equal to sigma plus IT. Okay. So this would mean that sigma going to 1 plus zeta sigma plus IT by sigma minus 1 whole power m, this is also non-zero, right? This will actually be C, the same C, well, some constant C, which you just take the Taylor expansion again around the point 1, and this is, you can let it I mean converge, I mean, so in particular you can take this limit of S coming on the real, I mean yeah, taking, that is fixing this, what you mean, wait a minute, you are going to say 1 plus IT, right? Here t is fixed because it is having a 0 at sigma plus IT, right? So once t is fixed, you can just move your S, that is only change the real part of the argument of this, but not the imaginary part. Okay, and that will give you just this one. It is basically this one, but now you are fixing a line through on which you are approaching the 0. Okay. Sigma minus 1, you don't need it, that's what I was saying here, because IT is fixed, right? So this is, I mean, this one has order of vanishing m in the denominator, right? And then suppose you were, I mean, taking S going to sigma plus IT, right? And that means this will have an order, I mean, order of vanishing m on the top, and this one has the same order at the bottom. Okay, so whatever term remains, it will not make a problem. Okay. So yeah, I mean, it will, they are having the same order of vanishing on the top and bottom, so they will cancel. Okay. Now that, so now both of these are not equal to 0, that you, okay, not equal to 0, sorry. Which one? T? Yes, because what happens at 1 we have already checked. So here we are assuming that T is not equal to 0, because in the, I mean, in the morning session we have already seen that at t equal to 0, I mean at precisely at the point 1 we don't have any problem, because we are subtracting this 1 by s minus 1, okay, from, so the function that we considered was zeta prime s by s zeta s minus 1 by s minus 1. Now since this has a pole of order 1 at s minus 1 with residue 1, so this, I mean, when we subtract 1 by s minus 1 from this is not having any poles anymore at s equal to 1. Okay, so we have to consider now all the other points, that is all the other points of the form sigma plus IT with t not equal to 0. Okay, and we are going to show that the zeta function is not going to have a 0 at any of this point. So what we are doing, we are assuming that it has a 0 at this, at such point, and we are trying to find a contradiction. Okay, equal to 0, yeah, we, as we have written, not sigma plus IT, 1 plus IT, excuse me, equal to 0, and then we'll draw the contradiction. Okay, so, and that will come from this thing. Let me write down a claim there, or maybe an exercise, but it's an easy exercise as well. Okay. exercise this is. So for all sigma greater than 0, excuse me, zeta sigma cube zeta sigma plus it whole power 4 zeta sigma plus 2it, this is greater than equal to 1. Okay, so now at a first glance it might seem rather difficult, but it's not if you prove a sub exercise before. So this may be exercise 1 and this is, yeah, you already have some idea to do this. Okay, if not, then let's take first exercise, well, a sub part of this. Okay, so some, okay, of the previous one, that is, consider, okay, wait a minute, first, I mean, actually this solving this exercise proves the prime number theorem. I mean, if you could prove this, then that would imply that zeta is non-vanishing on the real line, real part equal to 1. And let's do that part first, right? That is, let's assume this and show that this is the exercise that will finish the proof. Okay. Okay, so assume that, and then note that if this is larger than or equal to 1, we know that if we multiply this with sigma minus 1 whole cubed, take the limit as sigma goes to 0, this one goes to 1. If we multiply this whole power, I mean, sorry, divide this by sigma minus 1 whole power 4m, where m is the order of vanishing of zeta at this point, then not sigma not at this point, at 1 plus it. So let's assume that sigma 1 plus it is equal to 0, and zeta has the order of vanishing of zeta at this point zeta at 1 plus it is m. Okay, then what we do here, we multiply it with sigma minus 1, say. Note that this sigma, I mean, the claim is for real part of sigma greater than 1. Okay, so we will go, okay, for all sigma greater than 1, excuse me, thank you, real part of s greater than 1, that is just sigma greater than 1. Yes, so now this one, this will converge to 1, right, as we take sigma going to 1 from the right hand side. Similarly, here if we divide by sigma minus 1 whole power m, this will also go to some non-zero constant. Okay, and then set of sigma plus 2it, we have it here, but this entire thing was greater than or equal to 1. So whatever constant is yielded by this, some constant c, say, this will be larger than or equal to that constant, right? If this limit is, I mean, we'll write it down, okay? Limit sigma going to 1 plus uh, sigma minus 1 whole cube zeta sigma cube, that is equal to 1, right? Then you have limit sigma going to 1 plus sigma plus it whole to the power 4 by here 4m, excuse me, 4m. This is not just m, this is 4m. Earlier, I mean, because this has order of vanishing, this has order of vanishing m at this point, 1 plus it, right? So we need 4m there. Oh, and then it will be, I mean, whatever value this is giving, say c, this will be this power 4, because no, if we are taking already it with 4, then it will be just the same constant, excuse me. Okay, we know that it is converging to some limit, and I was just thinking of taking this divided by sigma minus 1 whole power m, so that would give us some constant. But similarly, if you take the entire thing power 4, this is giving you some other constant, okay, which is not equal to 0. So now the entire thing for sigma greater than 1 is, I mean, if you even if you take limit sigma going to 1 plus, this is giving you some, well, not some constant, but some constant times sigma minus 1 whole cube by this, right? Because on the right hand side you should also multiply with these factors that we have multiplied, okay. Sigma minus 1 whole to the power 4. Yes, but if it has order m, when I mean this m is for the order, I mean to compensate for its order of vanishing m at this point 1 plus it. We assume that it is not a simple 0 of I mean at 1 plus it, but at 1 plus it this has a 0 of order m. So that's why this m comes there. Yes, right. Yes, right. Yes, not c, c times this. I mean that was, yeah, that's why I wiped the right part, because this should be right larger than equal to the limit of sigma minus 1 whole cube by sigma minus 1 whole to the power 4m as sigma goes to 1 plus, right? Okay. And now these two are converging to some constant, right? And this one is having some value, I mean some, because zeta of 1 plus 2it, this, so zeta has only a pole at sigma equal to 1 and t equal to 0, right? So at this point t is not equal to 0, so it will have some value. It could be a 0, it could be a non-zero point, we don't care, okay. It cannot be a 0 because we are assuming that this is greater than equal to 1, okay. Oh, but that already means that um, wait a minute, I mean this is greater than equal to 1 for all the sigmas which are greater than 1, but at 1 plus 2 it, I mean this doesn't guarantee that at 1 plus 2 it there cannot be a 0. So there can be a 0 at that point. We are proceeding by contradiction, right? We are assuming that there is a 0 here, and from there alone we are getting a contradiction, okay. We'll show that how. So that means as sigma goes to 1 plus, the left hand side of this remains bounded, How about the right hand side? So what happens to the right hand side as sigma goes to uh, 1 from the right hand side? This one, is it which one, m? Yes, because if m is greater than or equal to 1, then the RHS goes to infinity, right, as sigma goes to 1 plus, right? Whereas the left hand side remains bounded. This one is converging to 1, this one is converging to some constant, and this one is taking some finite value. Okay. However, the LHS remains bounded. So thus we are getting a contradiction if sigma of 1 plus IT is equal to 0. Okay. So in other words, the Riemann zeta function doesn't have a 0 at the line where real part of S is equal to 1. Okay. Zeta S is not equal to 0 if real part of S is equal to 1. Okay. So now we see, is the logic clear to all of you? So now we see that the task remains is to prove this thing. Okay. So this is the final exercise that one should do to get that Riemann zeta function doesn't vanish on this line. Okay. Now how to proceed with this? Well, what is the absolute value of this? If you write this as e power, well, log zeta, okay, wait a minute. Even before going there, there are two sub exercises. Okay, so sub exercise 1, that is, show that the real part of log zeta s is given by summation lambda n by n to the power s log n times real part of log zeta s. Yes, so this would be lambda n times, so cos, yeah, if s is equal to sigma plus it, then this would be just cos of t n times cos of t. Okay. Or wait a minute, no, cos of tn. Okay, yes, that's right. And n is running from 1 to infinity. Okay. So first show this, and once you could show this, then we would apply this here. Okay. I mean, via the sub exercise 1, we should go to prove this. So how far are you? Did you already got some series for log zeta s? We used log zeta s also earlier, right, for showing that summation 1 by p diverges, right? And there, okay, we started with the Euler decomposition of this, right? So yeah, of course, here sigma is greater than 1 because we have the Euler decomposition wherever the function converges absolutely, right? Right. And then if you take log zeta s, this is just minus sum over p log of 1 minus 1 by p power s, right? Now if you expand this, you get sum over p, sum over r, and here inside you get 1 by r p power rs, right? I mean all the terms in this expression are negative, so this minus 1 just goes in and they're positive. Okay. And now would like to write it in terms of the von Neumann function. Okay. So von Neumann function requires a log in the, I mean for log PRS there should be a log P there, right? So let's bring that in first. P sum over R log P by R log PR. Oh, sorry. Okay, log PRS times log P, right? Okay. I note that this is just that n power s, okay, and where is this R? So there, what? Very nice. Yes, indeed. Yeah. So this is sum over P. Okay, then we can write this as sum over P, sum over n. Actually, just the von Neumann function, right? Sum over n. Upstairs we have lambda n, and below we have n power s log n. Because indeed, when we are considering p power r, then this is I mean p power r as our n, then this is n power s and this is log of n. R times this is just log of n. Okay, sure, thank you. So this log zeta s is, I mean, well, till now we have got right. There is a mistake in this one here. It should be n power sigma, because now we will take s equal to this s equal to sigma plus it. Okay. So that implies that log of theta s, this is equal to sum over n lambda n power sigma plus it log n. Okay, and this is sum over n lambda n power sigma log n, and this one is just n power it, right? Now we defined n power s as what? Exponential of s log n, right? So this n power it, well, if we take it on the right hand side, it will write n power minus it, right? That would be just e of minus it log n. Okay, e power minus it log n. Okay, So I see, there is another mistake. Okay, unless you do the exercise, you couldn't figure out where is the thing. Okay, so the angle here is t log n, right? So it should be cos t log n. Okay, so this one is summation n lambda n power sigma log n times sine of t log n minus I cos t log n. Okay, and you see, if you now yes, yeah, of course, yeah, that's the Dimavers formula, right? Very sorry, and that was the exercise actually. I mistook it. Okay, so this is cos t log n minus I sin t log n. Now, if you look at the real part of this, this just comes out to be cos of this times this, right? Okay, so we see that if the real part of s is greater than 1, then we have the real part of log beta s equal to summation over n lambda n by n power sigma log n cos t log n. Okay, so now to show this, we recall that this times sigma yt, this one we can just write them as exponential of log of, and only the real part of that those, because the other, I mean, the imaginary part will also all go to 1, right? So this would be just, I mean, well, to show that this is greater than equal to 1, it's equivalent to show that the real parts real part of log zeta s um, zeta sigma cubed log sigma plus it whole power 4 and wait a minute, real part of no, it's a is a product, right? So it there should be, yes, tell me, there should be sum, right? Yeah, real part of this plus real part of log of um, zeta times sigma plus it whole power 4. Well, whole power 4 can just come out here, it would be 4 times this plus real part of log of sigma plus 2it, this is this thing is greater than equal to 0, right? Just have to show this. and now that boils down to work with this kind of things. Okay, so let's write it down there. Okay, so this will be just 3 times, also this was a cube, so 3 times this, right, 3 times real part of log zeta sigma. Okay, so that would be just 3 times that. Okay, we are just going to use this formula. Okay, and here we say that lambda n by log n sigma, these are the, well, the 3 times real part means that 3 times this for sigma plus it. No, for sigma actually this t is equal to 1, so it is just t equal to 0, so cos 0 is 1. Okay, so only this part will remain. For the next one it will be 4 times this, and for the next one it will be just this one, but t replaced by 2t. Okay, so we have that, I mean this is equivalent to show that summation over n lambda n by n power sigma log n times 3 plus 4 cos t log n plus cos 2t log n, this is greater than or equal to 0, right. Now note that this is, I mean, well, just consider this one, 3 plus cos theta plus cos 2 theta, it is of this form, right. Okay, this is always greater than or equal to 0 for all theta. Why? 1 plus, okay, that is equal to 3 plus, here it is, wait a minute, there is 4 cos theta plus cos 2 theta is cos square 2 plus 2 plus, okay, so you just want to break it, right, 2 and 1, okay. Yes, and then, so, right, okay. Wait a minute, 2 plus 4 cos theta plus 2 cos square theta, yes, and then you just take 2 common, right. So this is equal to 2 times cos theta plus 1 squared, which is greater than or equal to 0. So that finishes the proof of the prime number theorem. Okay, okay, let's review the entire thing again, what we have done so far. There were several steps and the last step was actually trivial. So the proof of prime number theorem just depended on this thing at the end, that this is greater than or equal to 0, which was a trivial because the square is always greater than or equal to 0, right. Okay. So let's recall what we did so far. We wanted to show that pi x is equivalent to x by log x. We saw that this is equal to, I mean, equivalent to xi x being asymptotic to x, and this was being implied by the convergence of this integral xi x minus x by x squared dx go on to infinity. This integral converges, and the convergence of this was implied by the analyticity of a similar integral with the denominator replaced by t power 1 plus s instead of t squared, x power 1 plus s instead of x squared, excuse me. So this was implied by the fact that 1 to infinity xi x minus x by x power 1 plus s dx is analytic in the region real part of s greater than or equal to 1. Okay. And there, after this, we got this, showing that this was analytic in the region depending on showing that zeta prime s by s zeta s minus 1 by s minus 1 is analytic in this region. Right, yeah, minus. Okay. And this, well, at s minus 1 we saw that there is, s equal to 1, there was no problem. So this was equivalent to the fact that zeta s has no zeros, has no zero on real part of s equal to 1. Okay. And that was equivalent to the fact that zeta sigma whole cube zeta sigma plus it whole power 4 not equivalent to this was implied by to it whole power nothing, whole power 1. This is greater than or equal to 1 for all sigma greater than or equal greater than 1. Okay. And this one came from this fact. Okay. Cos 2 theta greater than or equal to 0 for all theta. Okay. So that was the entire, that was the outline of the entire proof of the prime number theorem. Okay. Logarithmic derivative. Yes. Yes, there is a Ayres and Selberg, but that is the real analytic proof of this. Every other proof uses the zero that is non-vanishing of zeta on the line s equal to 1. I mean real part of s equal to 1. Okay, now a small exercise for you. Okay, you recall in the first lecture, Professor Ritubroto Munshi mentioned Barton's postulate, right? That is, there exists a prime between n and 2n for all n. Okay. Well, if you allow n equal to 1, then even then there well, and between as less than equal to, then you still get 1 and 2 here, and 2 is a prime. Okay, but for everything higher, you get a prime strictly in between. Okay. Now, well, the prime number theorem is an overkill for this, because this could be established with Chebyshev's theorem with enough good bounds. Okay, but at least from the prime number theorem, can you obtain this? So that's the next exercise, that is, assume the prime number theorem and obtain this. Pi of, again tell me, pi of 2n. Yes. Oh, right, yeah. So what you may assume is that, well, let's write down the exercise clearly here. I have to allow you to choose n large enough. So it's say Barton's postulate, but for n sufficiently large. It is, can you obtain that? So this is this exercise that for n sufficiently large, show that there exists a prime p such that n is less than p less than 20. So use the prime number theorem to obtain this. Yes, how? Tell me. Okay, so insert consider pi of 2n minus pi of n, right? Okay. Okay, yeah, sure. So that is okay. So you want to do what after this? Tell me. Yes, asymptotically equal to this, but we need some inequality somewhere, right? I mean, we can. So pi to n is asymptotic to asymptotic to 2n by log 2n, and pi n is asymptotic to n by log n, right? And then do you require it goes to infinity? A positive lower bound. Okay. Okay, you think, but how to show that from there? That the prime number theorem, of course, implies that this is equivalent. That is, this is asymptotic to this is asymptotic to this, and then what? What does asymptotic to means? I mean, this symbol, what does it mean? Yeah. Yes, pi to n is, of course, big O of this, and what more? That is, pi n is, it is big O of this, means that it is less than equal to some constant times this, right? And I mean, that we already have from Chebyshev. Yes, we know that, right? Yeah. I mean, this divided by this, or this divided by this, as n goes to infinity goes to 1. That means that the the lim inf and lim sup are both 1, right? So you can conclude that, I mean, conclude a similar, some similar bounds like Chebyshev, but which are very very close to 1, right? Yeah, as close as you wish to 1, right? I mean, from this, that is the prime number theorem, just says that this divided by this, as you take the limit x goes to infinity, this is equal to 1, right? And that would mean that as you take x large enough, the ratio of this divided by this is larger than anything which is, I mean, even if you go a little bit to the left of 1, for sufficiently large x, that it is going to be larger than any 1 minus epsilon. I mean, choose any epsilon and it will be larger than 1 minus epsilon. Similarly, for x large enough, it will be less than equal to, I mean, the ratio of this divided by this as x goes to infinity, and for x large enough, it would be less than any 1 plus epsilon, right? So instead of this a and b in Chebyshev's theorem, you can now use 1 minus epsilon, 1 plus epsilon. So all you have to check what is the precise size of epsilon, which will give you that this distance is, and pi 2n minus pi n is positive. Okay, so please check that. Indeed, yeah. So suppose we have that in log n or x log x is less than equal to for x sufficiently large. Okay. We'll figure out what what's the relation between a and b, which will allow us to conclude that pi to n minus pi n is larger than 0. Okay. So note that pi to n is larger than equal to 2 a n by log 2n. Okay, and pi n is smaller than bn by log n, right? So pi to n minus pi n, that is greater than or equal to 2 a n by log 2n minus bn by log n, right? That becomes n. Okay, if you take n by log n out, yes, for any epsilon, sure. Oh, for 0, for any epsilon greater than 0, yeah, definitely you can choose some n, yes. But that 1 plus epsilon 1 minus epsilon, does this satisfy the condition that is necessary? That's a necessary condition, right? That this minus this should be greater than or equal to 1. So if you take epsilon on both sides, have you checked this is already satisfying this? Okay, let's see. Okay. So if you take n by log n out, what do you get? In the first part, you get 2a um, well 2a n is already out and there is divided by log 2n, right? So 2a times log n by log 2n, this minus b, right? That's what you were getting. And then this one is just log n by log n plus log 2n, right? Uh, Possibly we'll take log 2n out, that will make life easier. And everything will be clubbed towards b then. So let's take n by log 2n common, okay? That would give you 2a times, 2a minus b, and log 2n is out, so this is log 2n by n, right? And log 2n is log n plus log 2, right? So it will be just, okay, 1 plus log 2 by log n. This, this minus this is n by log 2n minus, times 2a minus this, right? And note that when n goes to infinity, this is going to be very small, okay? and log 2 is negative. So this is actually a little bit smaller than 2, sorry, smaller than 1, right? So all we require is that 2a is larger than b, right? 2a is greater than, even if it is 2a greater than equal to b, would that suffice? Let's check. And let's also once more check whether this one is perfect, right? It is just log 2n, so we have divided by log n, and this part is this one, that numerator is negative, right? Because so this is just a little bit smaller than 1. So that means that if 2a is larger than or equal to b, we are already getting something, um, some I mean this one should be greater than 0 if this happens, right? And so if you take, for example, this as some 1 minus epsilon and this one as 1 plus epsilon, all you require is that 2 times your 1 minus epsilon would be larger than equal to this 1 plus epsilon, right? And that is 2 minus, well, just 1 larger than equal to 3 epsilon. Okay. It is epsilon less than equal to 1/3. That would work, right? Okay. So, but we see that this is indeed an overkill, because 1/3 is, I mean, it's a quite a large thing compared to epsilon can go to as small as you wish. Okay. So Chebyshev originally used a, for Chebyshev he proved it with a equal to 0.921 something and b equal to 1.105 dot dot for x larger than or equal to 30. Okay. All right, and I mean he proved this inequality with these things, and he was able to derive this, what you call, um, the Barton's postulate from whatever he has proved as early as in 1852, way before the even Riemann wrote his memoir. So with that, we finish the afternoon session today, and tomorrow the morning session begins at 11. Of course, yes, we can. Yeah. Yes, sure. That will, yeah, that will, so, I mean, that will be, sure, yes. In fact, if you look at Chevyshev's, yes, and note one thing, that you don't have to choose the same epsilon on both sides, right? So indeed that would work. Okay. So that's all for today. We meet again tomorrow morning at 11. Thank you.